Since the Vietnam era, the world's tropic regions have continued to be the settings for violent conflict. These include the turmoil in Africa, in the Philippines, and in Panama, the conflict in Nicaragua, in El Salvador, and in Honduras, and the constant menace from Cuba. This escalating threat has increased the need to ensure the reliability and performance of military equipment in the humid tropics. The Tropic Test Center, located 9 degrees north of the equator on the Isthmus of Panama, controls about 3,000 acres of hot and humid land for testing. Within a distance of 50 miles, test sites typify microclimates corresponding to the variety of humid tropic areas found worldwide. Ranges and ammunition supply points that are controlled by the U.S. Army South are also available for testing. Exposure testing is conducted primarily at sites on the Atlantic side of the isthmus, which experience about 130 inches of annual rainfall, as opposed to the 80 inches of rainfall that is seen on the Pacific side of Panama. The Breakwater Site provides one of the most corrosive natural environments in the world, with its intense solar radiation, frequent and concentrated rainfall, salt spray, and winds. The coastal site is located just inland from the breakwater and is a more representative area for typical military equipment exposure to the elements. The open site is used to evaluate the combined effects of solar radiation and high humidity. Rapid temperature fluctuations associated with alternating torrential rain showers and intense sunshine between the showers is effective in breaking down the integrity of paints and adhesives that are weather resistant in less severe climates. Modern synthetic materials also exhibit progressive degradation in the humid tropics. Atmospheric salt and diurnal meteorological variations cause high corrosion rates. The Caribbean shore was used for the testing of these reverse osmosis water purification units. Inland from the coastal site, the forest site is immersed in the tropical wet jungle and is used to study the rate of biodeterioration for materials and equipment. The useful lives of natural materials such as cotton, wood, and leather are abbreviated when exposed to the humid tropic environment. Test items are subjected to short-term storage under representative conditions to determine if performance is degraded. Ammunition supply points on both sides of the isthmus are used for ammunition storage, exposure, and long-term surveillance tests, which include small arm ammunition, large tube ammunition, and missile items. During the TTC test of the Amitex explosive, the ammunition exuded a non-explosive ammonia compound. During the chamber test, conducted at 150 degrees Fahrenheit, TNT exuded. This misled the developer to believe that there was a problem when in fact none existed. During the first 2 tests of the 120 millimeter combustible cartridge case, hazardous burning residue was left in the tube because of water absorption during storage. Subsequent improvements eliminated the water absorption problem. The pursuit deterrent munition failed after the storage phase when mines were buried underground in plastic bags. Because of faulty packaging, moisture entered the mines and degraded the gas charge, which led to trip line deployment failures. Improved packaging, subsequently tested at TTC, eliminated this problem. The U.S. Army South firing ranges that are available as test sites include an overwater trajectory of 20 nautical miles and an altitude of 250,000 feet, rugged terrain artillery delivery sites, and level sites for airdropped munitions. Shown here in a recent volcano test, the Black Hawk, not itself tested in the tropics, suffered environmentally induced failures of electrical and electronic systems, corrosion of transmission/rotor installation, tail rotor installation, and other components. The mobility test areas that are located on the Atlantic side and the Pacific side of the isthmus provide a variety of natural terrain profiles, soil characteristics, and vegetation types and densities. Tracked vehicles were required to negotiate cohesive soft soils, extreme slopes, and obstacles common to cross-country operation in Panama. This mud, rugged terrain, and heavy vegetation can clog radiators, jam tracks, and severely limit the visibility of the vehicle operator. The Fort Clayton General Purpose Test Area consists of 40 acres of limited access forest and open field areas which provide a natural environment to support time-based exposure and performance tests. Exposure to this environment degraded the Hawk decoy and the shelter maintenance transportable to the extent that neither item could maintain its proper inflation pressure at the termination of their respective tests. Performance testing demonstrated that the high humidity degraded the performance of the chemical agent monitor. The XM5 static frequency converter was tested several times and was found to be vulnerable to moisture accumulation inside the protective case. This caused short circuits and eventual failure of the system. The validity of many tests are enhanced through the use of USARSO troops to determine the degree of military utility of the item in this environment. Tactical communications in the jungle are degraded because the dense jungle vegetation inhibits radio frequency propagation. POL collapsible tank tests are conducted at the Fort Clayton POL tank farm. The design of these tanks has been improved as a result of years of exposure testing in Panama. Tank material deterioration caused by exposure to rapid and regular surface temperature fluctuations, solar radiation, and humidity have been rectified to the point that tanks as large as 5,000 barrels are currently under test. The Human Factors Jungle Test Area is comprised of 2,500 acres of predominantly tropic forest. This area is dedicated primarily to obtaining objective data on the human factors aspects of Army equipment. Within the Gamboa area are the laser rifle quick-fire site, the ground-to-ground target detection site, a land navigation course, and the sound localization course. Insects, thick vegetation, steep terrain, and slippery soils are among the challenges presented by the Manpack Portability course. Dense tropic vegetation provides a haven for the enemy and presents a challenge to target detection. Heat, humidity, and terrain impose severe limits on physical activities and combat effectiveness. The soldier equipment environment interface of items such as the temperate battle dress uniform, the integrated individual fighting system, and various nuclear, biological, and chemical protective ensembles was evaluated using the courses available at this site. Test results here showed that the TBDU, the temperate battle dress uniform, was too hot for use in the tropics. Combat experience in Grenada corroborated this finding and prompted a congressional investigation. Of the individual fighting system components, only the vest was considered to be a suitable replacement for the standard item in this environment. The jungle canopy obscures or intercepts anything that must go through it. Steamed-up goggles and eyes stinging from dripping perspiration compound the soldier's problems. The NBC protective clothing caused severe reductions in operational effectiveness due to the soldiers suffering from heat stress. The Center actively supports the Small Wars Operation Requirements Division, SWORD, in its evaluation of equipment to meet operational needs for low-intensity conflict in the Americas. Testing of the unattended ground sensors at TTC provided data for Southcom IPR that resulted in the selection of the Miniature Intrusion Detection System, the MIDS, for limited production and user evaluation in Central America. Tropic Test Center support of SWORD includes the following projects. The Volcano Mine Dispenser is being developed to provide light divisions with a helicopter-delivered mining capability and to provide airborne and air-mobile forces with a ground vehicle-mounted mine dispenser that can be airlifted. The ultimate objective is to provide a single common mine and dispenser for both air and ground delivery. The Volcano System consists of a dispenser control unit, 4 launcher racks, and interconnecting cables. Mounting kits were developed for air and ground delivery vehicles. Each system can carry up to 160 mine canisters. Each canister contains 6 modified Gator mines, including 1 anti-personnel mine and 5 anti-tank mines. The anti-tank mines are detonated magnetically, while the anti-personnel mines are detonated by trip lines. Both mine types can be detonated by setting one of 3 classified self-destruct times. A certain percentage of the mines have anti-disturbance mechanisms. The system is designed to dispense minefields up to 950 meters long with a density of 1 mine for every 9/10 of a meter of minefield frontage. Smaller minefields can also be emplaced, as was the case during Tropic Test Center's test. The air system is mounted on the UH-60 Alpha Black Hawk helicopter. When fielded, 3 sets will be issued to each UH-60 equipped combat aviation battalion. The ground system can be mounted on a 5-ton dump and cargo truck. When fielded, 1 system will be issued to each engineer line company in light divisions, heavy divisions, and corps, and 2 sets will be issued to each airborne or air mobile engineer line company. Volcano testing to date included the Operational Test 2 conducted at Fort Lewis from July to September 1987 and the Developmental Test 2 which started in various locations during January 1987 and is now 90% complete. Limited production of the ground system started in the 3rd quarter of FY87. The full-scale production decision for both systems is scheduled for March 1988. The first unit is scheduled to be equipped in the 2nd quarter of FY89. The Tropic Test Center started its volcano test with a receipt inspection of the air system in May 1987. After flying a baseline performance mission in June 1987, the system was placed in its storage container for short-term storage until the end of September. In October and November, 6 mounting-dismounting trials and 5 performance missions were conducted. Then, the air system was returned to storage until June 1988, when the final performance missions will be conducted. Data from the 3 performance phases will be compared to determine if the system degrades from use and storage in the humid tropics. 6 mounting-dismounting trials were conducted, in addition to those performed for each mission. The Joint Service operational requirement for mounting-dismounting time is 10 minutes with 4 soldiers. An average of 25.8 minutes was required for a mounting trial, while dismounting took an average of 28.1 minutes. These times did not include the time required to perform certain additional actions, including the following: the replacement of the helicopter landing gear fairings with those contained in the Volcano set, the removal and replacement of the external store suspension system fairings, and the performance of helicopter wiring modifications. Problems identified during mounting-dismounting trials included the difficulty of mounting the heavy side panels with just 4 people, and the awkward location and design of the mounting bolts. These problems have caused hand injuries to personnel attempting to operate these mounting bolts. To prepare a test site for the Volcano air system, 2 large hills were removed from Empire Range 16 Alpha. This created a relatively flat area 550 meters long and 300 meters wide, an area large enough to test the dispensing of half of a mine field. After mounting the Volcano System and test instrumentation on the test helicopter and on a chase helicopter, pilots flew to Empire Range 16 Alpha, where air crews assisted in loading the canisters into the launcher racks. The upper racks were loaded with inert canisters to simulate the weight of a fully loaded system. The lower racks were loaded with test canisters. The blue canisters contained test slugs to simulate a 6-mine cluster from a canister, while the green canisters each contained 6 actual mines without the final explosive train. When the canisters were loaded, additional system tests were performed. If necessary, troubleshooting procedures were executed. When everything was otherwise ready, the crew chief set the mine self-destruct times and the dispensing speed on the dispenser control unit. After the canisters were armed, the helicopters lifted off. Pilots conducted several practice runs over the target area to coordinate procedures and to check instrumentation before flying the actual dispensing mission. As the test helicopter approached the range for the dispensing mission, the pilot tracked along the test range center line that was marked with 4 rows of engineer tape. The aircraft was brought to the altitude and speed prescribed for that particular test. From various locations on the ground, state-of-the-art photonic instrumentation was used to collect data on system operation and mine deployment, to include helicopter position as each canister was fired, helicopter response to canister firing, mine ejection, mine impact, and mine dispersions. These data were transmitted to a central control and telemetry collection facility. To begin the mission, the pilot keyed on the start lines and pushed the go-around button to start dispensing mines. The loading pattern of slugs and mines was designed to produce 2 distinct mine groups for self-destruct and for prime fuse functioning. In the air, a camera mounted behind the pilot's seat recorded the helicopter's speed, altitude, and heading. A camera mounted in the winch bay looked downward to measure the angle of sideslip and aircraft position relative to the intended flight path. These data were transmitted to the ground station by telemetry. The crew's conversations were taped for subsequent human factors analysis. The chase helicopter recorded the canister firing and mine ejection from the 2 o'clock position relative to the test helicopter. The mines armed a short time after being dispensed. Using a Tropic Test Center developed minecart, test personnel moved into the minefield to test the mines for prime fuse functions. Approximately 40% of the mines were tested for prime fuse detonation. The rest were tested for self-destruction. Here, a dud mine is placed into an ammo can for safe recovery. To prime fuse an anti-personnel mine, 1 trip line was pulled and the pressure required to function the mine was recorded. If the mine did not function, another trip line was pulled. Mines that did not detonate were left to self-destruct. Of the 26 anti-personnel mines tested for prime fuse, 8 failed for a success rate of 69%. To prime fuse an anti-tank mine, Tropic Test Center used a rough terrain forklift trimmed with armor plating. Mines that did not function on the first attempt were passed over for a maximum of 4 times. Those mines that failed to function were left to self-destruct. Of the 44 anti-tank mines tested for prime fuse, 16 failed for a success rate of 66%. Self-destruct times were documented by sound recording equipment and by mine watchers. The mines were designed to self-destruct between 80 and 100% of the self-destruct time set by the operator. 24 hours after the self-destruct time elapsed, all dud mines were cleared from the field and stored for fault analysis. Of the 169 mines tested for self-destruct functioning, 26 functioned early, 3 out of 5 mines functioned upon arming, and 45 did not function, dud mines, for a success rate of 58%. The location of each mine was surveyed. Data were plotted to determine mine dispersion patterns and minefield effectiveness. This diagram gives the viewer an idea of mine dispersion during one performance mission. The dispersion pattern was affected by soil strength, terrain elevation variations, standing water, and vegetation. Problems identified during the volcano air system test included the interface control panel, the ICP, which was not installed in an ideal location. To reach the controls on the panel, the pilot had to make an extra effort to bend forward. If the aircraft experienced tail rotor control problems, it would be very difficult for the pilot to respond to the emergency by jettisoning the ordnance in sufficient time. Circuit boards in the dispenser control unit were burned out during performance missions and had to be replaced. This previously identified problem is being corrected in production models. An intermittent problem with the jettison system caused one mission to be scrubbed and others to be delayed. This jettison cartridge housing failed all self-tests and was replaced. The crew chief found it very awkward to operate the DCU with his back towards the unit. The unit was installed at the right rear of the crew chief's seat, requiring him to loosen his seat restraining straps and to twist 120 degrees clockwise to reach the controls. TTC is also testing the volcano ground system. In December 1987, a portion of the ground system was mounted on a 5-ton truck for 5 days of open exposure, followed by a dispensing mission and dismounting trial and a return to storage for 3 weeks. This 1-week exposure, 3-week storage cycle will be performed a total of 3 times during the test. So far, no significant problems have been attributed to using or storing the volcano system in the humid tropics. However, the mine canister to be fielded with the system contains 5 anti-tank mines and 1 anti-personnel mine. This mix may not be suitable for use in many low-intensity conflict areas. Following POLIC Panama advice, Tropic Test Center has referred this observation to U.S. Southcom J5 SWORD. SWORD is investigating current doctrine pursuant to recommending a change in the anti-tank to anti-personnel mine ratio mix in the canisters.